Okay, so last time we finished with the following observation, that if you take the radical of any ideal, this is the same thing as intersection of all prime ideals that contain this given ideal I. So then we can give the following definition. The new radical of a ring R is the following thing. So notation is nil of R, and this is just the set of all nilpotent ideals. So I can as well just say that this is the radical of the zero ideal. So all nilpotent elements. Of the ring R. And of course, because we have this general observation for any ideal, we can conclude that the new radical of the ring is the same thing as intersection of all prime ideals. Okay, so this is one of the radicals of a commutative ring that we can define. So of course, if you just look at this remark, we can give the following definition. So the following definition will be also reasonable. What if you just take the intersection, not all the prime ideals, but only maximal ideals? So this is called the Jacobson radical. The Jacobson radical of the ring R is just by definition. So let's use notation J of R, and this is the intersection of all maximal ideals. So clearly there is an analogy between the definition of the Jacobson radical and the new radical. Now the question we want to analyze, how to understand Jacobson radical in terms of elements. So in terms of elements for the new radical, we have an answer. This is just all the important elements. So what would be the corresponding answer for the Jacobson radical? Okay, and by the way, before we do this, there is also a quite elementary remark that the new radical is always a subideal in the Jacobson radical. Well, of course, in general, they don't have to coincide, so the new radical can be smaller. Okay, so to analyze elements of the Jacobson radical, I also need another definition. So an element X in the commutative ring R is called quasi-regular if 1 minus this element is invertible. So I'm going to use just short notation R star for the set of all invertible elements, or in other words, all units of the ring R. So that's a definition of a quasi-regular element, and also I can give a definition of quasi-regular ideal. So an ideal I is called quasi-regular if every element of of I is quasi-regular. So this corresponds to, say, definition of a new ideal. Remember that, let me put it here, an ideal is called new ideal if every X in this ideal, so ideal I, is new ideal if every element is nilpotent. Okay, so first proposition that the Jacobson radical is quasi-regular. So what I need to show, I need to take any element x in the Jacobson radical, and I want to show that 1 minus x is invertible. Now suppose 1 minus x is not a unit, so not invertible. So we know that any not invertible element is contained in some maximal ideal. So then there is a maximal ideal, M, maximal ideal, such that 1 minus x is an element in this maximal ideal. But I know that x is an element in the Jacobson radical, and Jacobson radical as an intersection of all maximal ideals is contained in any maximal ideal. So what I see is that x is an M and 1 minus x is an M. So 1 is an M. And that's a contradiction, because then this M is not a proper ideal, M is just a ring. Now, next property, and by the way, remark, so we now know that every element in the Jacobson radical is quasi-regular. Is it true in the other direction? So is it true that any quasi-regular element is in the Jacobson radical? Is any quasi-regular element in the Jacobson radical? So what do you think about this question? So suppose x is quasi-regular, so 1 minus x is the unit. Is it true that this belongs to any maximal ideal? Actually, the question is elementary if you just look at the examples. What if I take ring Z?
Well, there's Jacobson radical is just 0.
Yeah, so in this case, of course, the Jacobson radical is 0. But you have, for example, quasi-regular element, which is 2. Right? Because 2 minus 1 is 1 and 1 is invertible.
Maybe if the ideal generated by the element is quasi-regular, then it belongs to the Jacobson radical.
That is actually a good idea, and that's actually what I want to show in the next proposition. So the next proposition, we have the following. So the Jacobson radical is the maximal quasi-regular ideal. So if you take a quasi-regular ideal, it sits inside the Jacobson radical. So proof. So if we assume that they have ideal I, which is not in the Jacobson radical, but quasi-regular. So this means that there is again maximal ideal, say M, such that this I is not in this maximal ideal. Okay, but if this I is not contained in this maximal ideal, if I consider the sum of the M plus this maximal ideal, so this will be ideal strictly larger than ideal M, so it has to be ring. And then it means that I can present 1 as the sum of two elements, say X and Y, so where X is an element in the maximal ideal M and Y is an element in the ideal I. And then if I look at the X, so let me finish the proof here. So X, which is 1 minus Y. So we know that we assume that I is quasi-regular, so 1 minus Y is a unit, right? And this means that we constructed an element which is invertible in the maximal ideal. So it's in the maximal ideal, and it's also a unit, so this maximal ideal is equal to the ring. Again, that's a contradiction. And finally, we can just combine this all together and get the following characterization of an element in the Jacobson radical. So X is in the Jacobson radical if and only if 1 minus xy is a unit. So let me just write in R star, and that is true for any y in the ring. So the proof just follows from what we already observed. So for example, in one direction, if you assume that X is in the Jacobson radical, then clearly product of X and Y, so I multiply on the right, maybe it's not quite convenient, but it's convenient to write xy instead of yx. So this is again in the Jacobson radical. But if this element is in the Jacobson radical, it means that 1 minus this element is invertible. And in the other direction, this observation that 1 minus xy is invertible just means that ideal generated by X is quasi-regular. Hence, it has to be inside the Jacobson radical. And X is an element of this ideal. Okay, so this is the end about radicals of the rings and ideals. So the next section, I think this is section 1.3, very short section, the so-called prime avoidance. Prime avoidance. So this is one of the classical lemmas in the commutative ring theory. So, and it says the following. So proposition, maybe even, let me call this theorem. Theorem about, sometimes it's called lemma about prime avoidance, sometimes it's formulated as a theorem. So let's call this a theorem because it's an important fact. So let I, so I can say that I is an ideal, but in fact in the proof I need a little weaker condition. So I is a subset closed under sums and products. So for example, an ideal will work in this situation, but in the proof I only need to be closed under sums and products. Now I also supposed to have a family of prime ideals. So and let P1, P2, Pn be ideals such that they all prime except maybe 2. So maybe P1 and P2 are not prime ideals, but P3, P4 up to the n are prime ideals. Okay, under these two assumptions I have the following. So if I sits inside the union of all PI's, then I sits inside one of these PI's. So for some index I. Proof? Well, first of all I want to reformulate this statement a little bit. So instead of writing I is a subset of the union of PI, then I have this, I can say that if I is not in any of these PI's, for I between 1 to n, then I is not in the union. Well, clearly this is the same statement. Right?
Why do we start from the third EL when we claim that we are prime? What is the meaning? Yeah, here. Such that P3, P4, and so on. We are prime, but we start with the index 1.
Mm-hmm. So we have
first two ones we are not prime.
Yeah, we have a family of ideals, and all of them are prime except maybe 2.
Mm-hmm.
So maybe P1 and P2 are not prime, but the rest has to be prime. Sometimes you can find a statement of this theorem a little bit weaker, saying that I is an ideal and all these P are prime ideals. So clearly this is a weaker statement, but I don't need these conditions in the proof, so what I need in the proof I stated here.
Okay.
Okay, so the first step is just rewrite the statement in an equivalent form, and this is clearly an equivalent form. Now I want to again rewrite this in a form that is more convenient for the proof. So I have the following: I is not in the PI for I between 1 to n. Then what this means that I is not the subset of the union. It means explicitly that there is x which is in the ideal, but x is not in the PI for I between 1 and n. X is not in the PI. Again, I think it's quite clear that the last condition is equivalent to the second condition, or the last implication is equivalent to the second implication. So now, why this is convenient? Well, because in the proof I want to construct this x. So the proof will be by induction, and in the induction, the goal of the induction is to construct this element x.
There's P contained in Py, then there exists X that not contained in Py. Oh, okay.
Okay, so now by induction, on the number of these ideals P, so number n. So of course the base of the induction when n is equal to 1, this is a completely trivial case. Now by induction hypothesis, so for I being between 1 and n, there is xi in the ideal I, and this xi is not in the ideal pj for j not equal to I. So now we need to understand why by induction hypothesis I can claim this. No, so xi is in the ideal I and not in all these ideals. So essentially I want to prove this statement for the n. I know that this statement is true for n minus 1, and I just apply this for all the indices in this range. So I know that this is true for n minus 1. So I apply this for this set of n indices without 1, without 2, without 3, and so on. And this is how we get all these statements. Okay. So first of all, we can assume clearly that xi is in the pi, right? Because otherwise, if you don't assume this, we finish with the proof. We constructed the element that we want.
From our assumption that we want to prove that we assume that there exists such an x, that it doesn't belong to pi, or I is such an x exists. But how is it connected to the formula written on this blackboard? But there exists such an xi, but doesn't belong to pj's or j's.
Yeah, because for example, I take this statement, I remove one of the prime ideals, and I know that this statement would be correct. And this will be true if I remove any of these prime ideals. So I just use all these statements.
But our ideal I isn't contained in the union of n minus 1 ideals. How can we use the induction?
Well, here's the statement. We don't need to say anything about the union. So I is not in any of these ideals. If I remove one of the ideals, this is still true. So the conclusion is still true. So this is why it's so kind of trivial reformulation, but I'm doing something on these steps because, well, this is equivalent to the given statement, and this is very convenient for the proof. Okay, so now I assume that xi is actually in the pi, because otherwise I find xi that works for n, not just for n minus 1. And now what I'm going to do, I'm just going to explicitly give you a formula for this x in the two cases. So in the case when n is equal to 2, I claim that I can take x be just the sum of these two elements. And this is not in the pi for I equal 1 or 2. So, and you can see that, well, for example, let's take I equal to 1, right? So why this is not in the P1? No, I assume that x1 is in the P1 and x2 is not in the P1. So this element is not in the P1. And the same will be for the second index. And you can see, to construct this x, the sum, I don't need to assume that I is an ideal. It has to be only closed under taking sums, actually. And I don't need to assume that this P1 and P2 are prime. I don't use this. I'm going to use these conditions for n greater than 2. So then in this case, the element that I take that satisfies this condition is the following. This is the product of x1 up to xn minus 1 plus xn. And again, I claim that this is not element in the pi for any I between 1 and n.
To the xn minus minus 1 plus x. Okay.
Plus the last element. Well, maybe because we already used this I several times, maybe to avoid any confusion, let me change this index to the L. So this is not in the PL for any L between 1 and n. Okay, now we consider cases. So the case L is equal to n. So I want to understand why this element, the product, plus the last element, is not in the Pn. Well, if I have that this product plus the last element is in the Pn, well, I already know that xn is in the Pn. So then the product of the elements x1, x2 up to xn minus 1 is in the Pn. But I know that the Pn is a prime ideal, so this is the case when n is greater than 2. So we can conclude that xi is in the Pn for some I between 1 and n minus 1, since this ideal Pn is prime ideal. But that's a contradiction. Let's contradict this condition. So this can't happen. Now we have another case. Case L between 1 and n minus 1. Well, if we assume that the product plus the last element is inside some PL, well, clearly this product, because it contains PL for which fix an index L, and there is element XL which is in the PL, so this whole product is in the PL. Well, this just because PL is an ideal. But if this is in the PL, the sum is in the PL, we can conclude that Xn is in the PL, and that's again a contradiction. Actually, I want to say that there is a situation when you already know this statement and you don't need to prove this again by using this proof. Well, what if R is not just any commutative ring? What if R is an algebra over a field, commutative algebra over a field, and this field is infinite? I claim that you already know this statement, right? That is because in this case, this P's and this I at least will be vector subspaces. And then the claim is that if you have a vector subspace inside the union of vector spaces over infinite field, then this subspace sits inside one of these subspaces. So this is standard fact from the geometry. But you need to have a field with infinitely many elements. Okay. So next section. So I promised that section 1.3 will be short with just one theorem. So next section is spec of a ring. So definition. This set spec of R of all prime ideals of R is called the prime spectrum of the ring R. So this is just a set of all prime ideals. Okay, now actually I want to put a topology on this set of all prime ideals. So this is called the risky topology. I start with the following. If I have an ideal, I in the ring is an ideal. So then I can define the V of I. This will be a subset in the spec of R, but this is by definition all elements in the spec of R such that I is a subideal of P. So V stands for the vanishing set. So essentially, if you, for example, assume that R is the polynomial ring, say for simplicity maybe in one variable, so maybe let's do an example. take the simplest possible example of polynomials in one variable. This is a principal ideal domain, so take ideal to be generated by some polynomial f. So then what's the v of this ideal? Well, I can say that these are all prime ideals. Well, I know prime ideals here. There's the zero ideal, and all other prime ideals will be just irreducible polynomials. Maybe let's, for simplicity, assume that K is algebraically closed. So then it will be all ideals of the form x minus some lambda, such that ideal f is contained in the ideal generated by x minus lambda. So of course lambda here is just an element in the algebraically closed field K. But this will just mean that this set the elements of this set are just the roots of the given polynomial f. So all the points where polynomial f is vanishing. And now we can generalize this for the case of the several variables, and at least if you just restrict your attention to the maximal ideals, if you have a polynomial ring, say, in many variables, you have an ideal generated by several polynomials, then this will be the set where this all polynomials vanishing. So this is why this is called v of I, v for the vanishing. Okay. Now I want to define topology in such a way that this v of I are closed subsets. And for this we need properties that this, well, first of all, that if I take, say, union of two, now this is again of the form v of something, but I can say this is the same as the v of the product and the same as the v of the intersection. We already know this. That was problem 1 on the seminar. So if this is closed, well, if the union of two such sets is again the set of the same form, this will be of course true for finitely many unions. So these v's are closed under finitely many unions. Now let's try the intersections. If I take v for the sum of the ideals, I claim that this is exactly the intersection of the v's of these ideals. And again, if you just think about this a little bit, you can convince yourself this is just clear, right? If you just remember that the sum of the ideals is the minimal ideal that contains all these ideals. And in this case, it could be any intersection, not necessarily finite, just any intersection. So, and of course, I also want to notice that the V of the ring is an empty set, and V of the zero ideal is just the spec of R. So I guess in this property number 3, I need to assume that I consider R as an ideal, right? Or I can as well say that this is an ideal generated by 1. So by looking at these 4 properties, you can conclude that V of I are closed sets in a topology on the spec of R, and this topology is called the risky topology. Okay, now let's analyze the following question. So what is the condition for the ideals that says that the v of one ideal is equal to the v of the other ideal? So for example, if ideal I is a subideal in J, well, clearly this implies that the v of J is a subset of the v of I. Just apply the definition. Now, how about if we go in the other direction? What if I know that the v of J is contained in the v of I? Can I conclude that I have this such inclusion of ideals?
The array which happens to be.
Yeah, so let's see. So for example, if I take a prime ideal from the left hand side, right? So J is contained in the P. I know that this implies that the I is contained in the P, right? So, but this implies that if this is true for any prime ideal that satisfies this first property, so it means that I is contained, or maybe they're equal, but so this is in the intersection of all prime ideals, because this is true for any prime ideal, with the condition that J is in this prime ideal, right? This is just the equivalent way to say that this is true, and because it's true for any prime ideal, I can take the intersection. This is still true, but now we can see that this is the radical. This is exactly the radical of the ideal J. So inclusion of the V's give me just the inclusion of the ideal I in the radical of the ideal J. And finally, what if I assume that the v of I is equal to the v of J?
And the radical side?
Yeah. So if you just kind of look at this previous line, previous observation, and combine this twice for the both inclusions, you can say this is equivalent to the statement that the radical of I is equal to the radical of J. So definition, an ideal I is called radical if I is just equal to its radical. So for example, we see that if you apply V to the ideal or you apply V to the radical of this ideal, you'll get the same thing. So there is a bijection between closed sets in the risky topology and radical ideals. Okay, and yeah, so maybe I can introduce some notation. So for example, if Z in the spec of R is closed, so this means that Z is V of something, and let's call this something I, maybe with the index Z. So this IZ is some radical ideal. Okay. So now I want to define the so-called principal open subsets. So let F be an element in the ring. Now we have D of F, or sometimes people use notation with the F as a subscript of D. So this is just open subset, which is the spec of R minus the vanishing set of the V. So D stands for doesn't vanish. So this is a set where element F is not vanishing. Okay, so this D is called a principal open subset. So why this is an interesting family of open subsets? Well, this is because this is the base of the Riski topology. So sets df form the base of the Riski topology. So to check that this is based on the Riski topology, I need to check two properties. So first of all, I want to show that if I take any point, and this point is inside some open subset, so this is in the spec R minus V of some I, so then I can put a principal open subset as a neighborhood of P, and this open subset will be also inside this open neighborhood of P. Okay, if you just look at this condition, so it means that this prime ideal P doesn't contain I, right? Just the same conditions here. Now, if this is true, then there is element, say F, which is an element in the ideal I, but this element F is not in the ideal P. Well, then we're done, because P will be an element in the DF, and this DF will be a subset of the same open set, spec R minus V of I. Okay, and the second property of the base is that if you take two elements in the base, right? Remember, take two elements in the base, take the intersection, take a point, you're supposed to have an open neighborhood of this point, which is also an element in the base. But in this case, this is a completely trivial statement, because this intersection itself is of this form. If you intersect df with dg, you'll get dfg. Which is again the quite elementary observation if you just go to the complements and look at the corresponding statements for the closed subsets. Okay. Now, in fact, this spec of R is not just some set, some topological space that we can associate with the ring. This construction is functorial in an obvious way. If you take a map between two rings, I claim that there is a map on the specs. So there's map spec F. This is quite long notation, so I'm going to call this just F with upper star. So this is a map on the specs that goes in the other direction. And what's the definition? Well, the definition is very simple. If you want to compute F upper star on some prime ideal, you just take the full preimage of this prime ideal. We know that the full preimage of a prime ideal is a prime ideal. So there is a map. Well, I think it's important to notice that this F upper star goes in the other direction. Right, because I started the prime ideal here, take preimage and get the prime ideal here, so for the specs it's in the other direction. Well, of course, this F upper star satisfies elementary properties, such as, well, if you apply, or if you want to, for example, take the identity on the ring R and then apply star to this, you'll get identity on the spec of R. And if you apply this star operation to the composition, well, say you have R mapped to the R prime, mapped to the R double prime, so this is F, this is G. Then you can compose G and F, take star, and just by the definition, this will be the same as the F star composed with the G star. Okay. Now, what's interesting about this F upper star is that actually this is a continuous map. So I want to show that this is a continuous map between spec R prime and the spec R. So I want to check that the pre-image of a closed set is again a closed set. Well, I just need to rewrite the definition several times. So what's the definition of the full pre-image? So this will be all the ideals P prime in the R prime, such that when I apply phi upper star to this P prime, I'll get something in the V of I. So then this is the same as the set of all prime ideals in the R prime, such that pi prime, so phi inverse applied to the pi prime is in the V of I. This is the same as all pi primes in the R prime, such that I is contained in the P inverse of the pi prime. Okay, now after three trivial steps, I have only one non-trivial step. So this condition, the last condition that I have here, the last property, is equivalent to the property I R star is contained in the P star. So this will be V of the I R prime. So believe for a second that this is true. Now we proved everything that we want, right? We proved that the pre-image of a closed set is a closed set, so it's V of something. So this would imply that phi upper star is continuous. So it's continuous map of topological spaces. So now the only thing that we need to check is that condition that I sits inside phi inverse of the P prime is equivalent to the last condition. Well, first of all, we haven't discussed this, but this is an ideal, right? So whenever you have a map between rings, you have two operations on ideals. You can start with an ideal in the R prime, take the full pre-image, you get ideal in the R. But you can also do the so-called extension of ideals. This is an example of extension of ideals. If you take the image of the F, well, if you consider something like this, no, it's not necessarily an ideal even. But you can take this, all these elements, and generate new ideal by these elements. So this, by definition, this is ideal generated by F of I. Well, maybe to be completely precise, I would need to write something like this: F applied to I and then product with R prime. But people just usually don't do this. This is not a standard convention to write this. For the extension of ideals, this is just a notation. So just use this as notation, but the meaning of this notation is an ideal generated by all the images. So at least this is an ideal. Now we need to understand why these two conditions are equivalent. Well, for example, if I assume that I have this, Well, then this implies if I take the pre-images, I still get inclusion of this form. Again, it is possible that they are equal. But I think it's not hard to understand that actually if you start with an ideal, you extend to generate something even larger than the image, and then you take the full pre-image, and why I use phi instead of f? Yes. So it looks like sometimes I use f and sometimes I use phi. So it should be f everywhere. Okay, but I think we get at least the statement in one direction. If you have inclusion like this, you take the pre-image, because when you extend the ideal, then you again kind of contract the ideal back to the I, take the full pre-image of this extended ideal, you get something that's clearly contain I inside. Okay, now we need to go in the other direction. So I assume that I is contained in the full pre-image of the B prime. Well, it means, for example, that whenever I apply f to any ideal, to any element of the ideal I, I'll get something from the P prime. That's the definition of the f inverse, right? If I have this inclusion, I have this inclusion. But if any element in the generating set sits inside this ideal, the ideal generated by this generating set also sits inside this ideal. So the end of this little explanation. So these two conditions are the same. And going back actually to the principal open subsets, they also behave nicely when you take pre-images. So if you apply maybe choosing phi instead of f was actually a better idea, because now let's call the map between the rings phi. Right? Because I already have f here in the notation, so if I want to understand phi upper star applied to the principal open subset df, or I claim that this is again a principal open subset phi of f. So this I leave as a little exercise, but it's not very hard. Just again go to the complements. Okay. So the next property is that, maybe before I go to the next property, I give a definition. So, not even definition, let's call this notation. Spec M of R, this is just the set of all maximal ideals. So this is just some set inside the spec of R. It's, of course, this thing is not functorial. There is no map.
Should it be phi star or phi star inverse? Or how does it work? Where does f live in R prime?
Inverse, right.
And it looks like f star.
What I wanted to have a full pre-image under this map. So I want to show that the open subset in the base is again open, and again in the base.
So f in the R.
No, F. Yeah, that's right. F is in the R. Yes. Okay, this is just notation because it's not a functorial construction, but it's useful notation. For example, instead of writing all the maximal ideals, say in the definition of the Jacobson ideal, I can now write something like this. The Jacobson ideal of R is the intersection of all M in the spec of M of R, M. And just to write something like this for the all maximal ideals, I want to introduce this notation. Now, the next thing I want to show about the spec of the ring is that the spec of R is quasi-compact. So proof. Well, in the proof I need to do the following. I need to take spec of R. I need to take any open cover. So open cover. And I need to choose a finite subcover, so finite open subcover. So first of all, I want to go to the complements, and if spec of R is equal to the union of these open sets, I can say that the intersection, so first of all I can say that any such open set is the complement in the spec of R to some V of some ideal IS. Now, if the union of all these complements is the whole space, then the complement, the empty space, is the intersection of these V IS. Right, so just going to the complements and use the same condition. So these two things are equivalent. And if I go back to my observation that the intersection is the same as the V of the sum, I have this. But if this is empty, the empty set is the same thing, say, as the V of 1. So what I have here is that the sum of these ideals is equal to 1.
So we start with spec R equal to, like, what is it equal to?
This is the union of open sets.
Oh.
So this is some open cover.
Oh, yeah.
To show that it's quasi-compact, I need to show that from any open cover, I can choose a finite open subcover. So that's what I'm doing. And I'm going to the complements, and the original condition is actually equivalent to the last condition.
Why would you use radicals in the last one?
Where do you want to put radical here? It will be...
Sets are good differently if the radicals of ideals are equal.
Yeah, if you want, I can write radicals here, but then I can remove the radicals. Again, this is something that we've done on the seminar, that this is an ideal. The radical of this ideal is the ring, if and only if this original ideal is the ring. But this means that this is a finite sum, say I between 1 and n. Fi and Fi is in the ISI, right? Because when we take the sum of any family of ideals, element in this sum is just a finite sum. So this one can be presented as a finite sum. So what you need to do, you just need to say that the spec of R is this finite union USI.
Can you repeat how do we get finite sum?
Well,
Is it finite?
no, this is related to the fact how you understand the sum of these ideals. If this is some infinite family of ideals, by definition, elements here are finite sums. such that, say, one component is one of these ideals, second component is another ideal, and so on. Because if you don't have any topology, it doesn't make sense to talk about infinite sums. We can only talk about finite sums.
Why do we consider finite sum
Hmm?
of ideals? Why do we consider finite sum of ideals?
Sorry, I don't understand the question. If you have a family of ideals, you can take the sum. This is again an ideal.
Why does this family is finite?
This is not a finite family. This is infinite family. But if you take any element in this sum for the infinite family, any element is a finite sum. By definition, this is how we define the sum of ideals. Right?
But it's clear.
But this is by definition the set of finite sums. So between I is running between 1 and n. So fi, such that fi sits in some I si. Elements here look like this by definition. That's the definition of infinite sum of ideals.
I mean, why does we consider finite number n?
No, because it's not possible to write infinite number. We simply don't have the separation. If you just take some formal infinite sum of elements in the ring, how you interpret this even as an element in the ring, not to mention some sub-ideal? So that's the definition. Well, remember that if you, when we discussed ideals generated by maybe, say, countably many elements, right? I can say this is the same thing as the sum of the principal ideals that would be one of the possible definitions. And here we only need to consider finite sums. Because this is the only thing that we can define, actually. There are no other reasons here. Okay, maybe you think about this and ask me later. All right, so we proved that spec of R is quasi-compact. And I want to finish with the topological definitions and exercises. So I'm not going to discuss these exercises even on the seminars. If you remember your elementary topology, you can do this exercises easily. Otherwise, you can just believe me. So the following conditions are equivalent. So exercise in topology. So for topological space X. So first condition is that intersection of any finite family non-empty open subsets is non-empty. Second condition is that any non-empty open subset is dense. And the last condition, any open subset is connected. So definition, a topological space is called irreducible. Quite important notion when you do commutative algebra and algebraic geometry. If satisfies conditions of the exercise. And you also can define a subset of a topological space to be irreducible if you just induce topology on this subspace, and this as the topological space is irreducible. I'm not going to write this. Now, second exercise about irreducible topological spaces. So Z is irreducible if and only if we have the following property. So Z is a subset in the union of the Zi's. So all these Zi's are closed. So if and only if Z sits inside of one of these Zi's. And then the last exercise, say this is 1 and 2, Z is irreducible if and only if the closure of Z is irreducible. Okay, this is some facts from topology that you need to know. And why we're interested in this here? Well, because I want to characterize irreducible subsets in the spec of R. And to do this, I need the following lemma. I'll take a point in the spec R, then the vanishing set, so I can think about this P as a prime ideal, so that's the point, and at the same time this is some ideal, so I can take the V of this ideal. And I claim that the V of this ideal P is exactly the closure of this point. Well, what's the closure of a set? Well, this is the intersection of all closed subsets containing this. So this intersection of all V of I such that P is an element in the V of I. Or in other words, this is the intersection of the V of I such that I is contained in P. Well, but as one of these elements in this intersection, you can take I to be equal to P. So V of P is here as one of the elements. So it means that this intersection at least is contained in the V of P, right? But then if we have this inclusion of ideals, we have the corresponding inclusion for the V's. So it means that whenever you consider element in this intersection, V of P is a subset here. So these two things are actually just equal. End of the proof. So we immediately have the following observation, that the closed points of the spec R are maximal ideals. Okay, so and I think this is the last proposition probably for today. So proposition a closed subset Z in the spec of R is irreducible if and only if this Z is a V of a prime ideal. Okay, let's prove this. So suppose closed subset is irreducible. Now I take product x and y in the corresponding radical ideal. Right, we know that there is a bijection between closed subsets and radical ideals, so there is a radical ideal corresponding to this z, and I want to show that this radical ideal is actually a prime ideal. So for this I take a product. So then of course the principal ideal generated by this product is a subideal in the IZ. And if I apply V to the left hand side and the right hand side, I'll get the following, that the Z is a subset in the V of the product. But the V of the product is the union of the V of X with the V of Y. So since Z is irreducible, we can conclude that Z is a subset in the V of X, or Z is a subset in the V of Y. So for example, consider the first situation. For the second situation, it will be exactly the same argument. So if we have this, then X, so again, I guess I need to go back to the ideals. So X is an element in the ideal X. Then I take the radical. Then this is the same thing as the IZ. I don't need to take radical 0 because this is already a radical ideal. So X is an element here. Or exactly by the same argument, Y is an element in the IZ. So if the product is in the ideal, X is in the ideal, or Y is in the ideal. So the ideal is prime. Now let's go in the other direction. Suppose P is prime. Now this is much easier. Well, we know that the point is irreducible. And if I take the closure, then this is again irreducible. Okay, so now we know all irreducible subsets in the spec of R, and these are exactly the prime ideals. And the bijection is essentially given by this. Okay, so this was the last proposition, and I want to finish with the definition. So I just don't have a better place to put this definition, and this has to be in the beginning of the course, because I'm going to use this again as convenient notation later. So the crude dimension of a ring R is the following thing. So let me just write dimension of R, and this is the supremum over all R's such that there is a chain of prime ideals of the length R plus 1. So for example, first example, well, maybe I just fix this. K is a field. So then in the first example, what's the dimension of K? 0. Second example, the dimension of the polynomial ring in one variable Yeah, so this is 1 because the maximal chain that you could have here is the 0 ideal sitting inside some principal ideal. So the length of this chain is 2, so the dimension is 1. And 3, we can try to show this by induction, but we can kind of postpone this until one of the last chapters of this course, that the dimension of the polynomial rings in n variables, this is as you expected, and maybe you can generalize 2.
You consider on prime ideals or on
These ideals are all prime ideals.
on prime.
Yeah,
Okay.
yeah, all these are primes. Now that is why I use notation P instead of just I. And by the way, a remark, you can use this definition in topology. You can start with any topological space and you can define dimension of a topological space, again as a supremum of all such, over all such irreducible subsets that form a chain. And I think this is called Norther definition of dimension, something like this.
Just look in some spaces which are normally used outside algebraic geometry.
No, it won't.
Irreducible,
Won't be a good definition. For example, if you take a Hausdorff topological space, then I guess irreducible subsets are exactly points, so it won't be a very interesting definition. But but for some topological spaces, for example, topological spaces that you see in commutative algebra and algebraic geometry, this works. And it's a reasonable definition. Well, this example actually shows that it's a reasonable definition. And I just want to generalize condition 2 a little bit. I wanted to take R to be principal ideal domain, PID, principal ideal domain. Then the dimension of R is again 1, exactly by the same computation. Okay, that's it for today. We continue next Monday.